Okay, hi everyone. Welcome to CS330. If you're not here for CS330, you're in the wrong place, but hopefully you're all in the right place. We're going to start with some introductions to get to know everyone. So I'm Chelsea. I am an assistant professor in the computer science and electrical engineering departments at Stanford, and I'll be one of the instructors of the course.
Hi, I'm Karol. I'll be also co-instructing the course together with Chelsea. I'm an adjunct professor here at Stanford and also research scientist at Google Brain.
We also have amazing CAs with us. We can do a round of introductions for all of them. So let's start with Raphael, who's the head CA.
I don't have a microphone, but I guess hopefully you guys can hear me. So I'm Raphael. I've been working with Professor Finn for the last year and a half, 2 years. I'm mostly focused on things like offline reinforcement learning, offline meta reinforcement learning, model-based reinforcement learning, and generally that sort of thing. So if you're interested in any of those, I'm happy to chat, or any other last questions. I'm always available, so feel free to email us, ping us on Slack, like post on that.
Great, Dylan?
Still a CS PhD student. I work on RL pretty broadly, but these days I do a lot of RL and information. Looking forward to being able to drop the course before.
Kyle?
Hi everyone, I'm a second year PhD student. I'm advised by Chelsea and Judge Blue. I focus mostly on learning for robotics, and welcome to the course.
Great. So with that, I think we can start the first lecture. Welcome everyone. It's really amazing to see people in 3D, in person. Of course, we're still in the middle of a pandemic, and so we understand that there might be various challenges that come up in the middle of the quarter and so forth. But it's really exciting to see everyone here, and we're going to try to be understanding and so forth with respect to different aspects of the course. For example, the lectures are being live streamed and also being recorded, and so if you have to miss a lecture or can't be at a lecture in person, we have everything available in that way as well. So first I want to just, hear how everyone is doing. So do you want to, raise your hand and say how you're doing? Could be one word answer, something longer. Yeah?
Pretty good.
Pretty good. Yeah.
Amazing morning.
Amazing morning? Yeah?
Excellent.
Excellent, okay. Yeah?
Lovely weather.
Lovely weather. It's pretty warm today. Yeah?
Excited to be back on campus.
Yeah, excited to be back on campus. Anything on the Zoom? Cool. Okay, lots of positive energy. This is great. Cool. Today we'll be talking about both some course logistics and then also why study multitask learning and meta learning. So first let's start with some course logistics. This is kind of boring, but it's good to go through all of this. Also, all the information is available on the class website as well if you have any questions or are not sure about anything that I talk about. So like I said, this is the course website. All the information and resources are available or linked on there or through Canvas. We're going to be using Ed for Q&A and discussion throughout the course. And this is connected to Canvas, and you should already be kind of automatically connected to that if you're enrolled in the course. We also have a staff mailing list if you have any questions that are kind of a little bit more personal in nature and not something that necessarily should go on Ed or shouldn't be visible to everyone or just to the course staff. Great, and then we also have office hours. All the information on office hours is on the course website, and the office hours are going to start on Wednesday. Cool. So for the topics of this course, we're going to talk about a variety of things, a lot of things that are listed here. Multitask learning, meta learning, the name of the course, including different kinds of meta learning algorithms like black box approaches, optimization-based approaches, and metric learning approaches. We'll get some more advanced topics and also some topics related to these kinds of techniques in the context of reinforcement learning. And then we'll also talk about things like lifelong learning, hierarchical RL, and open problems in the field. There are a couple things that will be new this quarter with respect to previous quarters. First, we're going to have a lecture on offline multitask reinforcement learning, which is a really important and more up-and-coming topic that I think is going to be especially relevant in the coming years and also a pretty exciting area. We're also going to have a guest lecture on learning optimizers, which is not a topic that we've covered previously, but I think is pretty exciting as well, and an expert from Google will be coming and talking about that. Of course, there'll be an emphasis on deep learning techniques. There are a lot of interesting techniques on some of these topics outside of deep learning, but the focus of the course will be on things related to deep learning. Then lastly, throughout the course, either through the homeworks or through the lectures, we'll have some case studies on various timely applications. This includes multitask learning in recommender systems, such as YouTube, meta-learning for things like land cover classification or in the context of education, as well as things like few-shot learning in GPT-3. There's a couple topics that we won't cover. We won't cover topics like architecture search or hyperparameter optimization, though a lot of the underlying techniques that we'll talk about will be kind of quite related to these topics. Okay, so for lecture and office hours, like I mentioned, we have in-person lecture. We also have live-streamed lecture and recorded lecture. The lecture is being live-streamed right now. Also, for if people aren't able to make it at the particular time, everything will be recorded, and you'll have access to the recordings through Canvas after the class. This could also be useful if you just want to kind of re-watch any part of the course. We're going to have two guest lectures. One is by Colin Raffel, who works on transfer learning in natural language processing. He's a professor at UNC and also spends some time at Hugging Face. And then we also will have a lecture from Joshua Sohl-Dickstein, who works on learning optimizers. During lecture, I really encourage you to ask questions. I'm not here just to talk. I don't really like hearing myself talk that much. I love hearing all of you talk, and I'm really here to help you learn the material, help you explore and learn about new topics and new areas. And everything becomes more interesting when you're asking questions too. If you have a question, you can ask the question by raising your hand. You could also enter your question into the Zoom chat, or you can also raise your hand in the Zoom chat as well. And then for office hours, we're going to have a mix of in-person and remote office hours. All of the instructor office hours will be in person. For the first 2 weeks, the TA office hours will all be remote because of university room scheduling challenges. But after that, some of them will also be in person. And because it's often useful to have different kinds of office hours, we're going to have a mix of pre-scheduled office hours and drop-in office hours that are managed with a queue. This can hopefully get the best of both worlds, where you can, if you have some things about like a project question, for example, that you know well ahead of time, you can schedule it ahead of time. But also if you have something that's a little bit more last minute or you want the flexibility, we'll also have drop-in options as well. Cool. So also some of the prerequisites. CS330 or something equivalent to a machine learning course is a prerequisite. And we also recommend some form of previous or concurrent knowledge of reinforcement learning. Reinforcement learning is covered in CS229 and CS221 and courses like that, and that sort of knowledge should be sufficient, and we'll try to fill in the gaps for people who are less familiar. All the assignments will be based in PyTorch, and so if you aren't familiar with PyTorch, we're going to be holding a review session. This will be over Zoom. PyTorch seemed to be what people preferred in previous quarters, and so that's a change that we're making from previous years in which the assignments were intense as well. Great, and then we're also going to have a couple other tutorial sessions. One is on variational inference. This will be useful for understanding one of the more advanced lectures on Bayesian meta-learning. And it's not required, but if you're interested in diving a little bit deeper into some of the topics in the course, this will be pretty relevant. And then we're also going to have a reinforcement learning review tutorial that will review some of the kinds of basic reinforcement learning topics that are covered in courses like CS229, CS221, if you have less reinforcement learning background. Great, and these are both either on a Thursday or on a Tuesday, and they're going to be kind of more towards the evening in general, and the kind of more information on the scheduling is available on the website and so forth. Great, so assignments. This is also something that's going to be a little bit new this year. We have an optional homework 0. One of the feedbacks that we had last year was that some students wanted to get a flavor of the kinds of things that they were going to be doing in the course pretty early, and get a flavor for the way that we approach the grading of the assignments. And so we introduced this assignment that just covers some of the basics of multitask learning. helps you check that you have all of the kind of necessary background knowledge for the course, and so forth, and are sufficiently familiar with PyTorch. We also have 3 homeworks that are kind of graded and required that cover multitask learning, meta learning, or multitask learning, meta learning, and multitask reinforcement learning. And then one final optional homework assignment on meta reinforcement learning. And we make this optional just because it's towards the end of the course, and a project, the project which I'll talk about next is one of the big parts of the course. And we want to make sure that you have enough time to work on the project and make progress on that. So the way that the grading will work is that it's 45% homework and 55% project. And so each of the kind of 3 required homeworks will be 15% of your grade. The first homework will be worth 2% of extra credit if you decide to do it. And the 4th homework will be kind of a full 15%. And if you choose to do it, it will either replace one of your homeworks or will replace part of your project grade. And we really designed this to try to give you some flexibility, and whatever we kind of, with regard to this last homework assignment, we're going to do whatever is best for your grade. And so, for example, if you do it and it makes your grade worse, then we'll just not count it for your grade. Great, and then we also will provide 6 total late days across all of the assignments, including project-related assignments, and a maximum of 2 late days per assignment. And this just helps us with grading things on time. Okay, and then lastly, the final project is a big part of the course. This is really a research level project of your choice that is related to the course material. You should do this in a group by yourself or in a group of up to 3 students. You're encouraged to use something that's related to your research if it's sufficiently kind of related to the topic of the course. And I think that it's great if you can kind of tie the 2 things together, and it often leads to more interesting projects as well. Also, you can share the project with other classes if you like, although we often will have a slightly higher expectation in that case. We're okay with this. If you also want to do this, you should check with the other course as well, based on their policies. And then lastly, it's the same late day policies as homeworks. There's no late days for the poster or the final report, and this is so that we can grade things on time before the university grading deadline. Great, and then we're also going to have a poster session. The time and location are still TBD. We're still working on reserving a venue for that. Cool, so those are most of the logistics. Are there any questions about the logistics? I know I went through a lot. Yeah? Yeah, you're welcome to collaborate with students who aren't taking the course. Part of the project will involve a collaboration statement, and so you should kind of write out the contributions of everyone, including people who aren't taking the course. Yeah? Sorry, what? Yeah, so you can either do it by yourself or in a group of up to 3 students. Any questions on Zoom? Okay, great. Well, if any more questions come up, feel free to put them in Ed, or ask one of us in office hours or something like that. As kind of initial steps in terms of getting started with the course, the first kind of optional homework 0 is posted, or if it's not posted, it'll be posted like within the next couple hours. And so if you want to get started on that, you can. And also, I encourage you to start forming project groups if you want to work on a group and start thinking about what you want to do for your project. Okay, yeah. Oh, great. So you're welcome to discuss the homeworks with other people, but we ask that you write up your solution independently, and including any sort of code and so forth. We also have more details on our honor code policy on the website, and you're encouraged to take a look at that. Yeah. Great. So now I want to talk a little bit about kind of why I think this course topic is really exciting. And I think that it's exciting for a number of different reasons. And I'm going to start by talking about some of my research and why I'm personally excited about a lot of these topics. Karol will then talk about why he's excited about the topic, and then we'll also kind of zoom out and provide a kind of broader perspective on why these topics are important and timely. Great, so one of the questions that I'm really interested in my research is how we can allow agents to learn a breadth of skills in the real world. And by agents, I mean actual physical robots in the world. So here are some videos of kind of some of the things that we've had robots do in my research lab. In this case, actually, this is I'm holding the block here. The robot learned how to place the shape sorting cube into the corresponding hole. We've also looked at scenarios where we want to have the robot be able to watch a video of a human do something and have the robot figure out how to solve the task. And also see if robots can figure out how to use tools in order to accomplish tasks as well. And I'm really fascinated by problems like this because robots, I think, can teach us things about intelligence. This might sound a little bit funny because robots aren't intelligent themselves, but robots are faced with the real world. They have to be able to generalize across different tasks and across different environments in order to be useful. They need some sort of common sense understanding in order to perform well. And also, supervision can't really be taken for granted. You have a robot like in a physical space, and it's not even really clear what the supervision should be. You don't have you're not given just a labeled data set, for example. And I think that all these sorts of things make it a really fascinating problem because a lot of these are like the things that humans are faced with when they're trying to learn and become more intelligent. And so first I start by kind of telling a little bit of story from here, which is that at the beginning of my PhD, there was a project that was trying to see how robots can learn. And I was kind of sitting in kind of an area right next to this robot. I was watching it learn like this. In this case, it's trying to learn how to assemble the toy plane, essentially. It's trying to learn how to place the wheels into the toy plane. And I think it's really fascinating because the robot is actually learning through trial and error how to solve the task. At the very beginning, it knew nothing about how to solve the task. And by the end, it actually becomes quite proficient at solving the task. That said, there was a bit of a catch, which is that the robot's had its eyes closed the whole entire time, and it was just doing this purely based on feel, essentially. And from there, a kind of pretty natural next step is, well, can it actually also learn how to see, as well as learn how to actually move its arms as well? And so that's what one of the first projects I did during my PhD was trying to see, can we have the robot learn through trial and error, both learning a perception system, essentially learning a neural network that takes as input images from the robot's camera and outputs torques applied to the robot's joints in order to solve the task. And you can see at the beginning, the robot was kind of just moving its arm around randomly. And over time, it's learning not just how to move its arm, but also how to kind of figure out where the box is so that it can put the block into the corresponding hole. And so you can see the kind of the final policy here, where I'm kind of holding the block out for the robot, and the robot's point of view is on the bottom right. And what was pretty exciting about this algorithm wasn't that the robot learned this one skill, but that the robot could learn lots of different skills. So it could use the same exact algorithm to learn something like putting the claw of a toy hammer underneath a nail, and like screwing a cap onto a bottle, for example. And also use a very similar algorithm to use a spatula to lift an object into a bowl. So this may seem like a little bit of a tangent. Overall, we were really excited about this sort of approach, but there was a kind of a pretty huge catch with all of this, which is that the robot in this case, what it had learned wasn't how to use spatulas to lift objects into bowls. It had learned how to use that spatula to lift that object into that bowl. And if you gave the robot a different spatula or asked it to do something else or gave it a different bowl or changed the environment, the robot wouldn't be able to solve the task. And this is a problem because ultimately we want robots to be able to do lots of different tasks and not just one very narrow skill. And so in many ways, this is the motivation in my mind behind trying to build systems that are more general and that can do many different tasks. So around the same time, people also use the same algorithm to do other skills like hitting a puck into a goal, like opening a door, like throwing an object to hit a target. And around the same time, people are also developing approaches for playing games like Atari or Go, or learning how to walk. But in all of these cases, they were learning one task in one environment starting from scratch. Now, you might say, okay, I know how to solve this problem. We just need to give the robot more spatulas, and then it'll learn how to do the task with many spatulas, and we need to give it more tasks, and it'll learn that, and so forth. But there's also a catch with that, which is that if you look behind the scenes in a lot of these learning processes, in many cases it looks something like this, where the robot tries the task, and then the environment needs to kind of be reset to some initial state, and then the robot tries the task again, and so forth. And one of the things you might notice here, this is my friend Yevgen, and Yevgen is doing more work than the robot is doing. And this is kind of silly. Like, we want robots to be able to kind of learn by themselves autonomously. And in this way, actually, Yevgen is like doing a lot of the work to do this learning process rather than the robot. It's not practical to collect a lot of data across a lot of different tasks in this way. And so we need new techniques in order to allow robots and other systems to learn many different tasks rather than just one task. So I've talked about this a lot in the context of robotics, but this isn't just a problem in robotics and reinforcement learning. If we look at a lot of the kind of state-of-the-art machine learning systems, a lot of them are specialized for one individual task, like translating between one language pair, or recognizing speech, or detecting certain objects. So these are often in more diverse settings, but there's still one task starting from scratch with pretty detailed supervision. And I'll refer to all these systems as sort of specialists in the sense that they're solving just a single task. And ultimately, we want systems maybe to be a little bit more like humans that are more like generalists that can do lots of different things and learn in richer worlds than the kinds of robots that I was showing before. And then one last note on this, in terms of my motivation, is that I think that if you look at a system like AlphaGo and a lot of the reinforcement learning systems that I showed before, they're somewhat analogous to essentially teaching a baby on day one to play Go. And from that standpoint, it's actually really silly to train systems specialized for a single task. It's kind of ridiculous to think that you can learn a single task really well without learning about other aspects of the world and so forth. Okay, and with that, Karol will come and talk about a little bit more about why he cares about multitask learning and meta learning.
Thank you, Chelsea. All right, so in my PhD, I was also working on robots, and initially I was working more on classical robotic pipelines, where we have a perception system that has to perceive the world, and then the robot has to look at the output of that perception system and do something in that world. And when I was working on it, I realized that it's actually really, really hard. So if perception system fails at some point and it fails in a way that the robot doesn't really know what to do with it, the whole system breaks apart. And at that point during my PhD, I attended a talk by Sergey Levin, who is now a professor at Berkeley, who started talking about similar things that Chelsea just talked about robots that learn through deep neural networks, that learn end-to-end, whole bunch of different tasks, and that interact with the environment and optimize the entire pipeline and learn how to do things. And I got really inspired by that, so I changed the topic of my PhD and I started working on deep reinforcement learning instead. And right now what really excites me is that I really want to see how the recipe that has worked in other fields, such as computer vision or language, the recipe where we apply modern machine learning methods to a field, and it is able to do really, really well in that field. How can we apply a similar recipe to robotics? So if we look at that recipe, it consists of two things. So first, we need a lot of data. For instance, the size of the ImageNet, 1 million images, so that we have enough data to optimize our neural net. Or in natural language processing, maybe we need all of Wikipedia. Anyway, we need a lot of data. And then we need expressive capable models that will be able to digest all of this data. So in computer vision, traditionally, these have been convolutional neural nets. And in language processing, these have been mostly transformers, now being applied also to computer vision and to many other domains. So if we just were to look at this and see what would it take to apply the same recipe for robotics, in terms of expressive capable models, it's actually fairly easy, right? We use very similar libraries. We can look at PyTorch or TensorFlow or anything else, take the best model that was applied to, let's say, natural language processing and just apply it to robots. But when it comes to data, it's a little more tricky. We can't just go on the internet and download scrape off a whole bunch of robotic data that is high quality where robots do a lot of things. But actually, I think it's a little bit more nuanced than that. And with a lot of data, if we look at some of the results in reinforcement learning, for instance, we actually do have a lot of data. So here is one example of the work from OpenAI of a robot learning how to operate this little cube here. And actually, the amount of experience that they had to collect in simulation was equivalent to 100 years. And we see in many reinforcement learning, robotic reinforcement learning experiments, that we actually do have a lot of data for these tasks. However, if we were to double the size of that data, of the data set, we would see that at some point the performance starts to plateau, and we don't really see much benefit in providing more data to the robot. The robot already mastered the task or learned as much as it could from that data set, extracted all the information, and even if we were to pour much, much more data, the robot is not really going to improve. It's not going to learn more about the world. However, if we look at supervised learning at the data sets such as ImageNet, if we were to double the size of that data set, I would bet that the algorithm would actually get better. And the reason for this is that ImageNet is much more diverse. ImageNet has many different categories, not just one category. It has images of things in the real world with different backgrounds from different angles taken by different people and so on. And I believe that's what we need for robots as well. We need to have data sets that are multitask data sets that consist of multiple robots in many different environments doing different things. So here I should be a little bit more precise and say that we don't just need a lot of data, but we need a lot of diverse multitask data. And in this course, we'll talk about what are the challenges associated with that, but also once we have that data, how can we utilize it best to learn multitask policies so that robots can learn how to do many different things, and how they can discover structure between these tasks so that learning each task is more efficient. And this is why I'm really excited about multitask RL and meta RL and all these things. So this is the reason that I usually give people why I work on these things, but there's actually the real reason that I want to reveal to you right now. So you remember this little video that Chelsea just showed of Yevgen resetting the puck and helping robot to learn how to play hockey? So there's actually one more person in this room. And this is the room. This is the robot learning how to play hockey. And this is me a few years ago with a little ponytail that I'm not very proud of, resetting the puck. And this damn puck, I spent so much time with it. And this was probably one of the lowlights of my PhD, spending the entire night resetting the puck. And I don't wish any PhD student to ever have to do this again. So please, let's work on multitask reinforcement learning so we can automate these things. All right, I'll move it over to Chelsea. Thanks.
Great. So that was kind of the perspective from robotics and a lot of the research that I do and that Karol does. But beyond robotics and beyond trying to build more general purpose machine learning systems, there's also a lot of other reasons to consider and think about these kinds of topics. So first, why should we care in particular about deep multitask and meta learning? Like Karol alluded to, before deep learning, there were these more kind of hand-designed pipelines for building AI systems. And so, for example, a system like this used something like these hog features that are hand-designed to try to pick out different kinds of features in an image, and then you would do some sort of deformable part model on top of that feature, which is another hand-designed tool, and then maybe you do a tiny bit of learning on top of that with an SVM. And with modern computer vision, this kind of changed the way that people approach the problem, and instead of trying to hand-design different aspects of a pipeline, they instead would just learn everything in this end-to-end fashion from data. And the reason why this recipe or this kind of second approach is really exciting is that it allows us to be able to handle unstructured inputs. It means that we can handle things like pixels, language, sensor readings directly rather than having to deal with, rather than having to assume that we have access to some more structured features that are extracted from these more unstructured inputs. And this means that we don't need hand-engineered features. We don't need as much domain knowledge as well. And as a result, these approaches are actually often much more applicable than approaches that require very detailed domain knowledge. And beyond not requiring domain knowledge, they also work really well. So if you look at ImageNet performance over multiple different years, you see there's a little bit of a phase transition between kind of right here, basically, in 2012. And that was AlexNet. And this was essentially really the first deep neural network that was successful in being applied to the ImageNet dataset, and really led to this whole phase transition and led to much better performance. And afterwards, everything after here is neural networks. And it's not just true in computer vision, also in machine translation. This paper by Google showed that you can apply deep neural networks to machine translation. And if you look at the performance differences between a kind of a phrase-based system, which is kind of a more hand-designed system, versus their neural machine translation system, you also see a pretty huge jump in performance. And this is actually, you also see a big jump in performance in tools like Google Translate because of the use of neural networks. Okay, so that's why deep learning. Yeah.
Images and text structured data.
Great, so the question was, are images and text structured data? And those are examples of things I would consider unstructured data. Because they are, they're just kind of the things, really the kinds of data that you would see that's very raw, that's directly recorded from a sensor or directly recorded from the internet. Forms of structured data would be more things like higher level features that are, like for example, whether there's a cat in the image or not, or kind of what the high level shape of an image is, or certain topics of an article, for example. Okay. So that's motivating deep learning. Hopefully there isn't too much more motivation needed for deep learning. Now, why deep multitask learning and meta learning? So there's several reasons for this. The first is that we've seen kind of this recipe of taking deep learning and applying it to large and diverse data sets and getting broad generalization. And we've seen this with ImageNet, we've seen it with transformers, we've seen it with Google Translate. But what if you don't have a large data set? There's a whole host of settings and applications where you don't have access to a huge data set right off the bat. This could be in medical imaging, in robotics, in translation from more rare languages, in personalized education, in medicine, and recommender systems, and so forth. And there's all of these applications that often the machine learning community may not be studying quite as much because they don't have these huge data sets, and we want to be able to apply and leverage the success of deep learning in settings like this as well. And for example, it's impractical to try to learn from scratch for every single disease or every single robot or every person or every language. Essentially, it's impractical to learn from scratch for every single task. And if we can instead pool data and information across tasks and from previous tasks, then this will allow us to actually apply deep learning and leverage the success of deep learning in these kinds of domains. So this is one example. In another example, maybe you have a large data set, but your data set has a long tail, where some parts of the data set you have a lot of examples and it's very well represented, and other parts of the data set is not well represented. You have only a small number of examples. So for example, if you look at the distribution of objects that a system has encountered, for some objects it may have encountered them a lot, whereas other objects it may have only encountered them once or a few times. And this might be true for a lot of different things. Maybe some people you've interacted with a lot and some people you've interacted with only a little. Or it could be the words that you've heard or different driving scenarios and so on and so forth. These kinds of distributions actually pop up all the time in real world problems that essentially follow this sort of power law. And this setting also breaks the standard machine learning paradigm where you kind of assume that you have a nicer distribution and that your train and test distribution match. Okay, so those are two reasons. As a third reason, what if you need to learn something new quickly? Maybe you need to learn something about a new person, about a new task, about a new environment, and so forth. To give an example of this, I'd like to give all of you a little test. And in particular, I'm going to give you a training data set, which are these 6 images on the left. And your goal is to be able to solve a classification problem using this training data set. And in particular, the 3 images on the far left are paintings that were painted by Brock. And the 3 paintings in the second column are paintings by Cezanne. And your goal is to try to look at these and learn from the 6 data points and ultimately be able to classify the data point on the right. And so after giving you a second to look at this, how many of you think that this is a painting by Cezanne? Raise your hand. And how many of you think that this is a painting by Brock? Cool. It's a little bit close, but I think the majority was for Brock. And that would be the correct answer. And you can, if you learn from this carefully, you can see that there's actually a lot of these kind of sharp contours in the painting, and you can use that sort of feature to recognize the style of Brock. I made this a little bit harder on purpose. If you look more at the colors, actually I think that you might guess Cezanne. But yeah, once you look at it a little bit more closely, you can figure out that it's Brock. Cool. So this was an example where if you just gave a neural network and you trained it from scratch on 6 examples, it would have no chance of being able to complete this task. And so this is what's called few-shot learning. And the way that you accomplish this is that you may not have seen these paintings before, or maybe even paintings from these painters, but you do have previous experience. You have previous experience maybe looking at different kinds of paintings. Your visual system is pretty good. It has previous experience as well. And you can leverage that previous experience along with the small data set in order to learn very quickly from just a few examples. Okay, so overall, some of the reasons beyond building more general purpose systems and allowing robots to be generalists for caring about multitask learning and meta learning include trying to solve scenarios where you don't have a large data set, where your data has a long tail, or where you want to quickly learn something new. So essentially, these are all elements where they're all scenarios where elements of multitask learning and meta learning can come into play. Okay, now I want to try to dive into a little bit more of kind of what do I actually mean by multitask learning and so forth, and what actually is a task. We'll define what a task is more formally on Wednesday, but for now you can think of a task as something that it has a data set and a loss function, and your goal is to learn a model that minimizes the loss function on that data set. And then different tasks can vary in different ways. Maybe the data set has different objects in it, for example, or maybe different people in it, different objective functions. So maybe the data set is the same, but you have different loss functions on it. That would be called multi-objective optimization. Maybe it corresponds to different lighting conditions or different words, different languages, and so forth. And the purpose of giving these examples is that multitask learning can refer to things that aren't just different tasks in the English sense of the word task. It can essentially correspond to things that would correspond more to like different domains or different objectives and so forth. They're essentially just different machine learning problems, and you want to combine those machine learning problems in a way that allows you to learn better. There is one critical assumption to basically everything in the course, which is that the tasks need to share some form of structure. And this is kind of the bad news, and if they don't share any structure at all, then you're just better off using single task learning because you're not going to be able to actually benefit from using data from other tasks. The good news, though, is that there are many tasks with shared structure. So for example, if you want to learn how to kind of open a jar versus unscrew a bottle versus kind of grind some pepper, for example, all of these have kind of a shared structure, similar motions, for example. And even if the tasks are seemingly somewhat unrelated, a lot of data has shared structure by nature of the fact that the laws of physics underlie a lot of real data, or for example, people are all organisms with intentions, or the rules of English will underlie all English language data, or even if you're learning across different languages, they might share similar purposes. And so as a result of this, this can lead to a lot more structure than purely random tasks. And it makes things like multitask learning and meta learning more general purpose and more applicable. Yeah.
Is it mathematically proven, or is it theory, or is it experientially like reached? What I mean is like, for example, our brain seems to have a single model learning all the tasks. Or is it proven that it needs to be different models learning different tasks that don't share a structure?
Yeah, so I guess the question was that it seems like humans have a single model that learns everything, and is it proven that they need to, that there needs to be some shared structure? I guess what I'll say is that if they don't share any structure, if they're completely independent, then you still can use multitask learning. It just means that it won't do any better necessarily than learning them independently. And so you still can use it. And in some ways it might be fine to use it. There are kind of practical challenges. So if you learn things that are completely independent, then you might need more capacity, or the network might have a harder optimization problem. But in principle, you should be able to do just as well as training a single model. I'll also try to give, I'll give a more formal definition of what I mean by structure in some of the coming lectures, especially when we talk about Bayesian models, which gives us actually a very nice language for talking about structure with respect to like independence assumptions, for example. Yeah.
Tasks share the same data set or have different data sets?
Yeah, so the question is, can different tasks have different data sets, or do they have to share the same data set? It can be either. You can share the entire data set and just have different labels, for example. You could have completely different data sets as well.
And another question is, how to verify if two tasks share same structure?
Great, so the question is, how do you verify if two tasks share the same structure? This is actually challenging, and this is in some ways a kind of an open research question in some ways. If we have time tomorrow, I'll try to talk a little bit about, on Wednesday, I'll try to talk about that question a little bit on Wednesday if we have time. Yeah?
Kind of a related question about shared structure. Is shared structure something that's like dynamic, like over time as we build better models, do we expect what counts as shared structure to expand, or is it percentage?
Yeah, that's a great question. It actually can be quite dynamic, and it can actually go in both directions. So as an intuitive example, say you want to kind of pick up a water bottle and pour, or maybe you want to pick up a clicker and click or something. If you don't know how to grasp objects yet, then they probably share a lot of structure because learning to grasp both of them is quite related. But once you learn how to grasp objects, they might actually start appearing very different because the task of clicking versus pouring are probably very different from one another. And so how much structure is shared may also depend on what the model knows as well. In the back?
Is there like an analogous requirement for multimodal data?
Is there an analogous requirement for multimodal data? So do you mean multiple data modalities? Yeah, so yeah, in general, you can also apply these techniques to multimodal data. For example, maybe you have RGB images and depth images, for example, and you want to learn from both of those. You do still need there to be some shared structure to learn from that. Also, you could also do single task learning in a multimodal setting by combining the modalities, and I wouldn't necessarily consider that as multitask learning, but there may be ways to formulate it that are related. Yeah?
Do you think the benefit in the multiple tasks come from the generalization ability of our neural networks, or comes from the common structure, shared types?
So you're asking, does the benefits of multitask learning come?
Do you think the ability of learning multiple tasks comes from?
So where does the ability to learn multiple tasks come from?
Yeah, so my writing is it can come from the generalization ability of our neural networks. So they can change maybe one network on this task and another task. And another guess is it comes from the common structure we utilize. So
Yeah, I think that both are important. I think that both the common structure is important as well as the neural network's ability to generalize. I think that the fact that neural networks can usually generalize very well within their data distribution is quite helpful. If they end up memorizing the data, then leveraging multiple tasks, I think, becomes more challenging. Yeah?
Do the networks need to share the same output space?
No, they don't. The question was, do they need to share the same output space, and they don't. You can essentially have an architecture that kind of potentially even splits into two outputs. Yeah?
Can a cluster of tasks be classified as tasks?
Can a cluster of tasks be specified as tasks? Yeah, so the definition of a task is somewhat fluid, and you could imagine scenarios where you even have hierarchies of tasks potentially as well, and there isn't necessarily like one ground truth definition of what a task should be. It could be something as low level as like, I don't know, grasping a tool. It could also be something at higher level like fixing a bike, for example. And it is something that is, it is rather, there's no like single definition. And that's why I like to think of it as something that takes as input a data set and a loss function and produces a model. Because this really puts it in more kind of concrete terms and allows the practitioner to define it appropriately. Great. So I'd also like to just briefly talk about some informal problem definitions. And again, we'll formalize this next on Wednesday. So what do I mean by multitask learning? In general, what I mean by this is trying to learn a set of tasks more quickly than trying to learn them independently from one another, or more proficiently than learning them independently. So you're given a set of tasks and you want to solve that set of tasks. And then the meta-learning problem is a little bit different. In the meta-learning problem, or at least the one that we're going to use in this class, you're given data on a set of previous tasks, and your goal is to learn a new task more quickly or more proficiently. And this is an important distinction because in the multitask learning problem, you aren't necessarily trying to be able to kind of adapt or learn something new. You're just trying to learn what you are given. Whereas in meta-learning, you want to be able to actually adapt to a new task. And this often means that you use a different kind of approach for solving this problem. And also say that these are the kind of the problem statements, and these are kind of different from the actual methods that you use to solve them. And then essentially in this course, we'll talk about anything that solves these problem statements. Yeah?
How is it different than transfer learning?
Yeah, great. So in transfer learning, I was thinking about putting this on the slide, but I decided not to. So in transfer learning, the transfer learning problem is very similar to the meta-learning problem. Sometimes also in the transfer learning problem, you're only given a single source task rather than a set of source tasks. But in many ways, the problem is basically the same as the meta-learning problem. The techniques or the methods end up being quite different. In meta-learning, you explicitly optimize for the ability to learn new tasks, whereas in transfer learning, the kinds of approaches often try to design things that will transfer well to new tasks, but they aren't optimizing for the ability to transfer. Yeah?
Will a multitask model always implement on a single task than a single task model given the same data?
Yeah, so the question is, will a multitask system always perform better than a single task system given the same data? And the answer is no. So sometimes multitask systems might run into optimization challenges, and that cause them to actually perform worse than a single task system, even trained independently on things. But in principle, you should be able to get to at least this level of performance as a single task system. And we'll get into the specifics of that in some ways on Wednesday. Okay, now you might be wondering, well, in the multitask learning scenario, where we want to learn a set of tasks, can't we just reduce this to single task learning? And in particular, what we could do is just take the union of all the data sets and take the sum of all the loss functions, and now you have a single data set and a single loss function, and you have a single task learning problem. So maybe we're done with the course. And in some ways, it can actually reduce to single task learning, which is great. You can just aggregate the data set and learn a single model. And this is a very reasonable approach to multitask learning. But we can often do better than this. And there are often techniques that we can use to either exploit the fact that we know that the data is coming from different tasks and leverage that assumption to do better. Or in the meta-learning scenario, we could actually leverage the assumption that we know that we want to learn something new and try to actually optimize for the ability to learn something new. And so what we'll be talking about in the course is how we can actually exploit that fact and how we can do better than just reducing it to a single task problem. Okay, and then the last thing I'll talk about is why we should cover multitask learning and meta-learning, why we should study that now. And the reason why I think this is important is if you look at some papers from the 90s, for example, they actually talk a lot about multitask learning and so forth. So they talk about how you want to potentially run training tasks in parallel while using some sort of shared representation. You want to leverage multitask inductive structure. You want to be able to generalize correctly even from a single training example, so this one-shot learning problem, or the possibility for a learning rule to learn how to solve new tasks. So a lot of these ideas actually existed in the 90s, maybe before some of you were born in some cases. That said, these algorithms are really continuing to play a fundamental role in machine learning research and machine learning applications. So as some examples, people have been applying these kinds of techniques to learn machine translation for lots of different languages rather than just a single language, trying to simultaneously learn how to translate 100 languages, and you can surpass kind of strong bilingual baselines. Colin Raffel, who is one of our guest speakers, authored this text-to-text transformer paper that solves lots of different tasks within a single model. And this is a model that's, I think, been quite popular today and so forth. We've seen examples in robotics, so the ability to learn from a video of a human to be able to solve a task in just one shot. And in many ways, a lot of these advances are actually powered by the fact that deep learning has been more successful these days with the power of GPUs and with larger data sets and more computational power. As another example in robotics is the ability to kind of learn across multiple different domains by training in lots of different environments to get a system that can actually generalize to the real world by training on all of those environments. And then as one last example, a paper that we'll actually cover on Wednesday is multitask learning in YouTube recommendation systems that try to actually optimize multiple competing objectives for ranking the videos. Okay, and these algorithms, I think, are also just playing not just an important role in research and so forth right now, but they're also playing an increasing role in machine learning research. It's a little bit difficult to measure the role that they're playing in research, but we can look at measures like search queries and citations, and we see a trend that is going upward, and people are getting more excited and interested in these approaches. Also, if you look at kind of citations of papers that are related to transfer learning, meta-learning, and multitask learning, we also see increasing interest as well. And then lastly, I think that the success of these kinds of algorithms will be really important if we care about making deep learning accessible to lots of different applications and lots of different people. So if you look at a lot of the data sets that are used in the machine learning community, it's things like ImageNet, WMT, Switchboard, and so forth. And all of these have really massive data sets. They have 1.2 million images or 40.8 million sentences or 300 hours of labeled data. And if you contrast this to other problems that we also care deeply about, like diabetic retinopathy detection, this data set has 35,000 labeled images, which is drastically smaller than the data sets before. Or if we want to look at epilepsy treatment, this paper used less than 1 hour of data. Or in kind of an example from a robotics paper, we used less than 15 minutes of data. And if we want to be able to learn from small amounts of data, we should try to leverage other data sets and larger data sets and learn how to leverage those data sets in a way that allows us to transfer and solve these other kinds of small problems with small amounts of data. Yeah?
Can you perform both meta and multitask learning on the same network?
Yeah, so the question is, can you perform multitask learning and meta-learning on the same network? In often cases, meta-learning algorithms will actually also learn how to solve the training tasks. And so in that sense, yes, you can. Okay, and then the last thing that I'll mention is that this is a field that is, like I mentioned, is growing in interest and so forth. And so we also still have a lot of open questions and open challenges. And in many ways, I think that this is what makes the field so exciting. There's lots of really new problems to solve. And so there'll be scenarios potentially in this course where maybe you'll ask a question and it's kind of an open problem in the field. And maybe that means that it's a project that you should investigate in your project, for example, or something that, that we'll see in future work applied. Great. So that's it for the main content of today. It'll be a bit of a shorter lecture, I think, than future lectures, which will take up the full 80 minutes. As a couple of reminders, the first optional homework is out, and also encourage you to start forming project groups. And I'm also happy to take any remaining questions if there are them, or you can come up to the front as well.